Hello viewers, myself Dr. Girish Hampanawar, KLA College of Pharmacy, working as assistant professor in the Department of Pharmaceutical Chemistry. So in this particular session, we'll be continuing with the remaining session or the remaining part of fluorimetric discussions, which we started in the previous episode. So the previous episode was had a discussion regarding the introduction, definition, theory, and how the fluorescence and the phosphorescence phenomena were happening. So in this particular session, I would like to take up the factors affecting fluorescence, and there are several factors which definitely affect the fluorescence phenomena, and I would like to discuss these factors one by one. So before we go for the actual discussion of the factors affecting the fluorescence, I would like to bring your attention for the phenomenon of fluorescence and the structure or the chemical structure or some of the parameters that are related with the structures and its fluorescence phenomena. So we need to understand something called as quantum yield or quantum efficiency. This quantum yield or quantum efficiency is a parameter that is used to measure the probability of the molecule whether that possesses fluorescence or phosphorescence. So quantum yield is defined as an efficiency of converting absorbed light into emitted light. So the fluorescence is all about the emission of the longer wavelength radiations as the molecule is excited by an UV visible radiation. So we have two different wavelengths. One is the excitation wavelength and the other one is the emission wavelength. The excitation wavelength is always the shorter wavelength, which is in the UV visible range, and the emission wavelength is usually the longer wavelength region, which is accounting for the fluorescence or the phosphorescence. So the quantum yield is a measure of probability whether the molecule will show the fluorescence or the phosphorescence or not. So if the molecule is highly fluorescent, then the quantum efficiency usually will be 1. So if the molecule is not showing any fluorescence, or if it is not possessing any fluorescence property, then the quantum efficiency will be usually 0. So that is how the quantum yield or the quantum efficiency measures the probability of a molecule showing fluorescence or phosphorescence. So the fluorescence rarely results from the absorption of UV visible radiation at the wavelength as short as 250 nanometer, because the radiation at this particular wavelength is so high energy or so high in energy that it deactivates the electron in the excited state just by pre-dissociation. So the fluorescence is rarely visible at the wavelength below to 250 nanometer. That is because this wavelength is having so enough energy or so high energy that will deactivate the electron in the excited state by a phenomenon called as pre-dissociation. Pre-dissociation is the relaxation that is enough to break the bond. Okay, so pre-dissociation is the relaxation to a state with enough energy to break the bond. So if you use wavelengths less to 250 or 200, then that wavelength will be having high energy, and that energy usually breaks the bond rather than bringing about the fluorescence or phosphorescence phenomena. So the bond of some organic molecules, as I mentioned, would rupture at the higher wavelength regions or even at 140 calories per mole. So for this reason, the bonds which are responding at this higher wavelength regions, particularly the sigma to sigma star transition, this transition is rarely involved in fluorescence phenomena. I mean to say, we have 4 different transitions which we have discussed in the UV visible spectroscopy. This sigma to sigma star transition is rarely observed in fluorescence phenomena. Instead, the lesser energetic transitions like pi to pi star and n to pi star transitions are much involved in fluorimetry. The reason for representing pi star to pi is because fluorescence is all about from coming back, or since it is an emission phenomena, it is the simple journey of an electron from the excited state to the ground state. I mean to say, it is the pi star, which is an excited state, to the pi transition, which is a bonding state, and pi star is an anti-bonding state. So these two, pi star to pi and pi star to n transitions, are much involved in fluorescence phenomena. In most fluorescent compounds, radiation is produced by these two, pi star to pi or pi star to n transitions, depending on which requires the least energy for transition to occur. And fluorescence is most commonly found in the compounds in which the lowest energy transition is pi to pi star, excited single state, than n to pi star, which suggests that the quantum efficiency is greater for pi to pi star transition. So higher the quantum efficiency, then more probability of the compound or the molecule showing the fluorescence. So what this whole paragraph means is the fluorescence phenomena is most commonly found in the compounds in which the lowest transition, that is pi to pi star, excited singlet state, than n to pi star, which is involving the triplet state, whereas the pi to pi star involves excited singlet state. So the quantum efficiency is much high for pi to pi star transitions. With respect to phosphorescence, it is exactly the opposite of fluorescence, wherein which the n to pi star excited state happens, wherein which the electron enters the metastable triplet state, which tends to be short-lived and less susceptible for deactivation than pi to pi star triplet state. So this is where the fluorescence is happening in the molecules which have pi to pi star transitions, and phosphorescence is happening in the molecule which shows n to pi star transitions. The most intense fluorescence in compounds is found in compounds containing aromatic group with low energy, that is pi to pi star transitions. A few aliphatic acyclic carbonyl and highly conjugated double bond structures also exhibit fluorescence phenomena. Most unsubstituted aromatic hydrocarbons also show fluorescence in solution form, and the quantum efficiency, as I mentioned, increases as the number of rings or the degrees of condensation increases. So the quantum efficiency, if increases, the probability of molecule showing the fluorescence increases, not the phosphorescence. So as I mentioned, if the number of rings and the degrees of condensation, if they tend to increase, then the quantum efficiency increases, then the probability of the molecule showing fluorescence also increases. Some simple heterocycles like pyridine, pyrrole, furan, thioprene do not exhibit any fluorescence. With nitrogen heterocycles, the lowest energy involved or the lowest transitions is involved in n2 pi star system that rapidly converts to the triplet state and prevents fluorescence. So this whole sentence, it means that any molecule which is containing nitrogen as a heteroatom, if there is a nitrogen, these nitrogens have unpaired electrons, and these n electrons will bring about n to pi star transitions. And if there is an n to pi star transition possibility in a molecule, then they simply show phosphorescence, rather they do not show any fluorescence. So that is, we say that it prevents the fluorescence but shows phosphorescence. And also fused ring structures will show fluorescence because there is involvement of more and more pi to pi star transitions. For instance, a fusion of benzene ring with heterocyclic structure results in an increase in the molar absorptivity of the absorption band. The lifetime of the excited state in a fused structure and fluorescence is well observed here. So the fusion of ring will enhance the fluorescence, and it increases the quantum efficiency. For example, fluorescent compounds like below, which is quinoline, isoquinoline, they tend to show fluorescence because there is a condensation of one particular ring to the benzene, and this particular ring with the benzene, and this particular ring with the benzene. So any fusion will add up to the pi to pi star transitions, and these pi to pi star transitions will increase the fluorescence phenomenon. And fluorescence is favored in molecules with rigid structures. I have two structures here. Okay, let me not bring the cursor here. Okay, I have two structures, which is the fluorine and the biphenyl. You can see there is a difference in the rigidity of these two structures, whereas the fluorine is more rigid because the two benzene rings are attached with a 5-membered ring so that there is no flexibility in the molecule. Whereas if you see the two benzene rings which are joined by one single bond, which is biphenyl, there is a lot of flexibility of rotation of these two phenyl rings across this single bond. So biphenyl is more flexible, whereas the fluorine is more rigid. That's why the quantum efficiency of fluorine is high, and the probability of this molecule showing the fluorescence is excellent. Whereas the biphenyl, since the quantum efficiency is 0.2, the probability of this molecule showing fluorescence is very, very, very less. So with this preamble of the structure and fluorescence, we will come back to the factors that affect the fluorescence intensity. So we have all these factors which can affect the fluorescence intensity. Just to read them: nature of molecule, nature of substituent, effect of concentration, adsorption phenomena, nature of incident light, and the methods how we illuminate the incident light or illumination, presence of oxygen, change in pH, photodecomposition, temperature, and viscosity. So we'll take up these factors that affect the fluorescence intensity one by one. Coming to the first one, that is the nature of molecule. We know that in the previous discussion, in the previous slides, we just now saw that not all the molecules show the fluorescence phenomena. Only molecules which absorb invisible radiation and have pi to pi star transitions show fluorescence phenomena. Greater the absorbance of the molecule, the more intense its luminescence, whether it is fluorescence or phosphorescence. So more the absorbance of UV radiations by the molecule, more intense the luminescence is visible. Molecules having conjugated double bonds, especially the pi bonds, show fluorescence. Molecules like aliphatic and saturated cyclic organic compounds do not show any fluorescence. So we need to have a bit of unsaturation in the molecules so that they are fluorescence or they show fluorescence phenomenon. Coming to the nature of substituents, what these molecules have, in a case where the electron donating groups are present, usually these electron donating groups, they enhance fluorescence. For example, NH2, OH, etc. Whereas the SO3H, NH4 and alkyl groups do not have much effect on the fluorescence and the phosphorescence phenomena. The reason being the electron donating groups will donate or they enrich the molecule with electrons, and the electrons are the one which take up the energy and go to the excited state, and they bring about n to pi star or pi to pi star transitions. And in the molecule, if it is rich with electrons, then it is more a possibility that the quantum efficiency of the molecule is higher and higher, so that they show fluorescence with a high probability. If there is an electron withdrawing groups or halides, they decrease or even sometimes they destroy the fluorescence. The reason being vice versa. They simply withdraw all the electrons, making the whole molecule deficient of electrons, so that no electrons are involved in the transitions. And if that is the case, then the molecule will lose its fluorescence property. So some examples of electron withdrawing groups are COOH, NO2, and this N double bond N, etc. If a high atomic number atom is introduced into the pi 2 or introduced on the molecule or into the pi electron system, it enhances phosphorescence and decreases fluorescence. This is a very interesting observation. The reason being, there is a phenomenon of intersystem crossing that is observed with the molecules which are having a high atomic number substituents, and these high atomic molecules bring about n to pi star transitions, so that there is an intersystem crossing. We have discussed this intersystem crossing in the previous discussion, and this intersystem crossing results into the electron entry into the triplet state or metastable triplet state. Rather, fluorescence is not visible, but the phosphorescence is visible. So this is all about the nature of substituents on the given molecule. Coming to effect of concentration, fluorescence is directly proportional to concentration, and this is only to the low concentrated samples. Here you can see the fluorescence intensity is directly proportional to the concentration. And One more thing where we should understand is with the stronger solutions, the fluorescence tend to concentrate more and more at the irradiated phase of the cell. I mean to say at the surface of the cell or the sample holder. So this we usually come across when we are dealing with the quinine sulfate solution in a very high concentration, and that is why the fluorescence is much followed when there is a low concentration of the sample being considered. So coming to adsorption, extreme sensitiveness of the method requires very dilute solution, as I mentioned, 10 to 100 times weaker than those employed in spectroscopy or UV visible spectroscopy. So the concentration of the samples, what we prepare here in fluorimetry, it is much dilute when compared to the UV visible spectroscopy. Adsorption of the fluorescent substance on the container walls create serious problems. That is one of the reasons what we discussed just now, where in which the quinine sulfate tends to concentrate on the surface of the irradiated face of the cell, and that will usually interfere the linearity observations of the quinine sulfate or the standard calibration observations of the quinine sulfate. Hence, strong solutions are usually avoided, and they are rather much diluted. Coming to the nature of incident light, the monochromatic light is very essential for the excitation of fluorescence in the quantitative work, because the intensity will vary with the wavelength. The reason being the usage of monochromatic light is the monochromatic light is a light which is made up of one particular wavelength in spectroscopic terms. So for excitation of fluorescence in the quantitative work, this wavelength we need to keep it very fixed. We should not vary this particular wavelength. So the nature of incident light should be such that it should be always monochromatic in spectroscopic terms. Even when strictly monochromatic light is ensured, a further possible source of error is the Raman emission from the solvent, which is in some case quite unavoidable. Coming to the method of illuminations, there are two methods which we can follow. The first one is the right angle method, and the second one is the frontal method, which is just like the visible spectroscopic instrumentation. In the right angle method, wherein which we arrange the detector and the light source in the right angles, so that when the light falls on the sample cuvette, rather than keeping the detector here as we do in the frontal method, we rather prefer to keep the detector at right angles to the source of radiation. And this method is useful to give smaller blank values for scattered light and fluorescence. So the moment the incident light is made to fall on the sample which is showing fluorescence, the fluorescence will happen in all the directions. But if you tend to keep the detector here in the frontal method, the incident radiation as well as the fluorescent radiation both will tend to fall on the detector. In order to avoid that the emitted radiation to fall on the detector, or rather only to account the fluorescent radiation, we prefer to keep this detector right angles to the source of radiation. So the frontal method we can use if the solution is opaque or much cloudy. Coming to the effect of oxygen, the presence of oxygen will usually interfere in two different ways. One way is it directly oxidizes the fluorescent substance, which may lose the fluorescent property and may turn to non-fluorescent product. And the second way in which the oxygen may affect is by quenching of fluorescence. This quenching will be discussed in the separate heading in the next session, so that I won't be taking this dealing in much detail in this particular slide, but rather I would like to say quenching is something where it is a phenomena which decreases the fluorescence intensity. So one example where the presence of oxygen is much affected is the anthracene, a molecule which is very much susceptible for oxygen during fluorimetric analysis. Coming to the effect of pH, Any alteration of pH of the solution will have significant effect on the fluorescence if the absorption curve of the solution is changed. I mean to say, any change in the pH will significantly affect the fluorescence phenomena. An example I have taken here is the phenol, which is fluorescent in both dissociated and undissociated forms. Consequently, the fluorescence from the phenol will try to show two different peaks because of the dissociated and the undissociated forms, and or one from the ionic and the non-ionic forms. And that's the reason the phenols, if you take alter the pH of these phenols, then we tend to see two different peaks. That is because by the virtue of non-ionic and ionic forms. So effect of pH is very crucial because that tends to ionize the sample, or it tends to bring separate ionic nature, wherein which in UV spectroscopy these ions or the ionic configuration of the molecule will tend to change or will bring a change of absorption or absorption behavior, or will bring change in the fluorescence behavior. Coming to the next one, that is photodecomposition. Excitation of weakly fluorescing or dilute solutions with intense light sources will cause photochemical decomposition of the analyte. I mean to say, if we excite the weakly fluorescing or the dilute solutions with high intensity radiations, when we say the high intensity UV radiations, they have high energy, which will tend to break the bonds, or which will tend to bring about decomposition or light induced chemical decomposition, which we also call it as photobleaching. So that is one particular factor that affect the fluorescence phenomena, and this can be minimized by several ways. One being use of longest visible wavelength for excitation that does not introduce light scattering effects. I mean to say, we can use the longest visible wavelength for excitation, which does not introduce any light scattering effect. And the second way you can minimize it is measure the fluorescence immediately after excitation to decrease the duration of excitation. So simply bringing down the duration of excitation and measuring the fluorescence immediately after excitation, we can avoid this photodecomposition process, or we can avoid accounting for this photodecomposition process. Protect the unstable solutions from ambient light by storing them in dark bottles or amber colored bottles that we usually do. And remove dissolved oxygen from the solution by deaeration techniques, wherein which we remove the dissolved oxygen, and this is how we can reduce the decomposition in presence of light. And that this decomposition process will introduce a non-linear response curves and loss of majority of the sample fluorescence. So simply the decomposition will tend or it will make the fluorescent compound, and it will turn the fluorescent compound to a non-fluorescent product, which may not show any fluorescence. In way, this photodecomposition is a sort of quenching. It is a sort of quencher technique wherein which we tend to lose the fluorescence intensity of the given molecule by the decomposition process. And the last being in today's discussion, the temperature and viscosity, wherein which variations in temperature and viscosity cause variations in the frequency of collision between the molecule. If I vary the temperature, if I vary the viscosity, that will vary the frequency of collisions between the molecules. If I increase the temperature, I tend to add up the energy, or if I decrease the viscosity, I usually favor both. I mean to say, if I increase the temperature, I add up the energy to the molecules, and simultaneously, if I decrease the viscosity, this whole thing, or increase in temperature or decrease in viscosity, will decrease the fluorescence by deactivation of excited molecules by a simple process called as collision. So if I increase the temperature, the molecules will gain the internal energy and they will tend to collide with the neighboring molecules, and the fluorescence intensity will be lost by collision. And also decrease in viscosity will lead to the collision of the molecules or the excited molecules, and any collision of these excitation molecules, or the excited molecules, if they are losing up the energy in the form of collisions, not in the form of emitted radiations, then this collision energy is accounted, and this particular energy which is lost as a collision uh, contributes for uh, the decrease in the fluorescence intensity. So this is a type of quenching which we observe just by increasing the temperature or by decreasing the viscosity. So these were all of the factors that were affecting the fluorescence intensity. In the next session, I would like to consider the quenching phenomena, or the quenching of fluorescence, which is a very important topic, so that I will be taking that as a separate topic. So thank you very much for your patience listening.